A certain class of posets that we're going to find very useful is the class of unit interval orders. Let P be a poset. And let's let S be a subset of the elements of P. We call a poset Q on S a subposet of P if X being less than Y in Q implies X is less than Y in P. And we call a subposet, well, an induced subposet of P if X is less than Y in P, if and only if X is less than Y in Q. So for example, let's look at this poset on 5 elements. And let's let S be the set 1, 2, 4, 5. So if we define Q1 like this, and Q2 like this, then both Q1 and Q2 are subposets, but only Q2 is an induced subposet. So in Q1, every relationship between two elements here does come from the original poset, let's say P. But 2 and 5 are related in P by 2 being less than 5, and they're not related in Q1. Here, every single relationship between two elements that was in P is captured in Q2. So that's why Q2 is an induced subposet. It involves all possible relationships between the elements that we've chosen. Now let's look at two posets in particular and 4 elements. Let's call these posets 2 plus 2 and 3 plus 1, because those are the cardinalities of the chains in them. We call a poset in interval order if it has no induced subposet isomorphic to 2 plus 2. And we call an interval order a unit interval order if it has no induced subposet isomorphic to 3 plus 1. Could also call a poset avoiding 2 plus 2, 2 plus 2 free. Then unit interval order is, well, it's 2 plus 2 free because it's an interval order, and it's 3 plus 1 free. The reason for this terminology involving intervals is that we can define a poset on a set of intervals by saying one interval is less than another interval if the greater number of this interval is less than the smaller number of that interval. So if B is less than C. And then the resulting posets are precisely the 2 plus 2 free posets. Let me draw a picture of one. So for example, let's look at the set of 4 intervals, the interval from 1 to 2, the interval from 3 to 4, the interval from 5 to 6, and the interval from 2 to 5. So the Hasse diagram is, so 1, 2 is less than 3, 4, which is less than 5, 6, and 2, 5 touches 1, 2. Even though it touches at one point, they become incomparable. 2, 5 obviously touches 3, 4 because it contains it, and then it touches 5, 6 at the endpoint 5. So 2, 5 is incomparable to all of these three. And that is the poset 3 plus 1. And whatever collection of intervals we choose we're going to get a poset which is 2 plus 2 free. And conversely, for any 2 plus 2 free poset, there's a way to come up with a set of intervals to represent it as a poset of intervals. Now you'll notice that I used the same size intervals for these intervals, and then that one is bigger. Now if we restrict all intervals to have the same size, say 1, then the resulting posets are precisely the 2 plus 2 free, 3 plus 1 free posets. These results are due to Scott and Supps in 1958. So for example, if we look at the set of intervals 1, 2, let's say 3 halves, 5 halves, 2, 3, 5 halves, 7 halves. See, so 1, 2 overlaps with this interval. It overlaps with that interval at the endpoint. So 1, 2 is less than 5 halves, 7 halves. So we get 1, 2, 5 halves, 7 halves. 3 halves, 5 halves intersects both of these. 2, 3 intersects both of these and that one. So we get a poset that might call 2 plus 1 plus 1. Because it's a disjoint union of chains. And sometimes with disjoint unions of chains, we just name the sizes of the chains. Now the only 4-element posets that are not unit interval orders are 2 plus 2 and 3 plus 1. Now there were 16 4-element posets that we drew in another video. The fourth Catalan number is 14. So if we take away these two, there's Catalan number many posets left. And it turns out that the number of unit interval orders on n elements is 1 over n plus 1, 2n choose n, the nth Catalan number. Now the proof is by bijection, although the validity of the bijection is not obvious just by looking at it. So So the proof idea, and I'm going to leave a lemma or two for homework. Is that we're going to label the elements of the poset 1 through n in a strategic way. And then we're going to define a matrix or associate a matrix to the poset. By setting the aij entry to be 0 if I is less than j, and 1 if I is not less than j. And then we're going to be able to count the matrices. All right, let me tell you about this strategic labeling first. So for each element, define a number alpha of x, which I call altitude of x, to be the number of elements less than x in the poset minus the number of elements greater than x in the poset. And then label the elements in order of weakly increasing altitude. So we break ties arbitrarily. Let's call this an altitude respecting labeling. So for example, let's look at a poset that has 2 maximal elements, three minimal elements, and relations like that. By the way, a maximal element in a poset is an element that doesn't have anything else above it. And the minimal element in a poset is one that has nothing less than it. So let me write the altitudes of these elements next to the elements. So here we've got 0 less, and then 1, 2, 3 above. So that's -3. 0 minus 3. Here we have 0 less, and again 1, 2, 3 elements above it. -3. Here we have 0 less and only one element above it. -1. And the central element has 2 elements less and then only one above. So 2 minus 1 is +1. This element has 2 elements less than it and nothing above. So 2 minus 0 is 2. This element has 3 elements, 1, 2, 3, 4. 4 elements less than it and nothing above. So its altitude is 4. So we can label the elements 1, 2, breaking this tie arbitrarily. And then the next lowest altitude is here, 3. And the next one is there, so that's 4. And the next one is here, so that's 5. And the next one there is 6. So the only freedom we had was we could swap the 1 and the 2 and the elements that had the lowest possible altitude. Now this labeling is natural in the sense that if one element is less than another, then its label is less than the other label. So x is less than y in the post set, then that means that the label of x is less than the label of y as integers. But that doesn't mean that every natural labeling respects altitude. So here's another natural labeling, because every time we have one element less than another, its label is less than the other. But this one does not respect altitude. Right, now I said we're going to associate a matrix to the post set. The matrix is going to have a 0 in the ij position if I is less than j. That's going to have a 1 otherwise. So the matrix in this example is, so we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1 is incomparable to itself, and 2 and 3. It's less than 4, less than 5, less than 6. 2 is incomparable to 1, itself, 3. It's less than 4, 5, and 6. 3 is incomparable to 1, 2 itself. It's incomparable to 4, incomparable to 5, and less than 6. 4, I think I said incomparable here. Yeah, it is. Okay, 4 is greater than 1 and 2. Incomparable to 3. equal to itself, and comparable to 5 less than 6. So we have 0 for less and 1 for anything else, either equal, greater than, or incomparable to. So 5 is not less than anything, and 6 is not less than anything. So this is the matrix we get. And if you believe that matrices are all going to have this form with the zeros in the upper right and the ones below, then it's easy to count these, because the path between the ones and the zeros is basically a lattice path, which we know are counted by the Catalan numbers. So the crucial part of the proof, with which I'm omitting, which should be a lemma, is that when we use an altitude respecting labeling, this matrix has the special form with the zeros and the ones that has a lattice path between them. So altitude respecting labelings of unit interval orders give the nice arrangement of zeros and ones in this matrix, which is called the anti-adjacency matrix. Anti-adjacency because the ones and the zeros are placed maybe in the opposite place than what you would expect. And in this part of proof, we can make part of a group homework. The end.